Good day, everybody, and you're most welcome to today's presentation. This is one of our fortnightly CNPS so-called alternative sessions, where we go into a little more depth in regard to problems with regard to modern physics, or problems as far as the speaker sees them. Now, today we have a most interesting presentation entitled Newtonian Electrodynamics. And excuse me, without wishing to be presumptuous with regard to what the speaker is going to be talking about, I might say that this is a subject dear to my own heart, because I've looked at this for some time now, and I found it quite interesting that Newtonian dynamics, which basically works in the world at large, and sent men to the moon and so on, and the Galilean transformations between coordinate systems is quite intuitive, and it works. There's been a problem when maybe at the end of the 19th century people were applying these transformations to electrodynamics. And I've sort of thought in some of my analyses I've called the Lorentz transformations I've called them Oshos, which is a polite way of saying that they're just a quick fix really for something that's originally wrong. Now, so I'm quite interested in seeing what David has to say about this. David has been a minute or two getting in and getting the slides ready, but he is here. So I'll bring him up in a second. Nick wants to say something. Okay, seems urgent.
Yes, I believe that Professor Isis will be joining us, and he and David DeHilster have had quite a lot of exchanges. And David was, among other things, a big fan of Professor Isis, and also was grateful for him to introduce him to the work of Karazani. So I just give that as a little bit of background.
Okay, well, thank you very much. I think David may say something about that, because David, since you raised it, Nick, David has actually invited Professor Assis, and he's invited Neal Graneau to the talk. And he said, may I, do that? I said, we'll tell them they're cordially invited on behalf of the moderator, because I am aware of the very significant and impressive work that Professor Assis has done. And of course, Neal Graneau is one of the partners. He's the son in the Graneau's work, which David will be looking at. I think up to date, up to the moment, as Nick says, there's quite a strong possibility that Professor Assis will attend, but we've had no verification from Graneau, although David might update me on that. So basically, just to say that the works of Dr. Peter Graneau and his son Neal Graneau, Dr. Neal Graneau, they've done this work on Newtonian electrodynamics, and indeed they've written a book on the subject. And David is going to give us his own analysis and exposition of that. So, David, I'm delighted you're here. We've no video. Do we have audio?
Yeah. Can you hear me?
I can hear you. We can hear you perfectly. But is there a problem with your camera?
No, I just checked it. You can hear me though, right?
I can hear you. Yeah.
Let me. I have this nifty new webcam. Let me just see if I just checked it on the camera.
Yeah. It's not absolutely essential. It'd be nice if we have it.
Is that the camera setting for Windows shows me perfectly? I don't. Can you see me now?
No. It just says GoPro.
No.
Your name.
That doesn't work. GoPro doesn't work. Let me see. Let me try settings here. just love Windows. Mac is so much easier to use, in my opinion.
Oh, right. Well, people who are used to it say that. Yeah, 5, 6, 7. I
Cameras.
see Nick has allocated a further space in the green room. Although we only have 7 at the moment, and we have a maximum of 10. But I think once your slides are put up, that might take one space.
So I'm in settings on Windows and under Bluetooth and devices, and it says connected cameras.
Yeah.
Logit 270 HD webcam.
But if you
you need to be under settings in StreamYard. There's a little icon that says settings there, and then that will let you pick which camera to use.
Where will I find that icon?
In StreamYard, it's in the very bottom row. It's like you see leave studio, present, stuff like that, mute. Do you see that?
I see. Okay, I've got the screen that's showing you and Ian Cowing and a little thing that says GoPro.
Yeah, and below that, I think you should see there's some icons in the bottom row.
It says you're in the show.
A banner that says mute, stop cam settings.
Okay, let me pull this up. Okay, yeah, I see it. Mute, stop cam, leave. Go under settings here.
You should click
Setting.
Franklin.
Oh, I see it. Logit.
Click settings.
Let's see here. Okay, so now it says device not connected.
Yeah, that's right.
Let's.
Device is not connected.
Well, hopefully you have to go in, and then you can select which camera and microphone you wish to use. Apparently, he may have multiple, but he may have clicked.
But David, we can't hear you now. You're completely disconnected, as far as I can see. So the audio is gone as well.
Okay.
Now it's maybe coming back. It's gone again. Whatever's happening. Sorry, ladies and gentlemen, in the general audience for this messing around. If you just give us a few minutes, we should have it cleared up, hopefully. It says that they will need to connect their mic cam at the stage. You're up again, David, so we probably have audio.
Can you hear me?
You can hear you now, yes. There's a different icon. It's sort of, no, you've gone again. Whatever you did there. We could hear you for a second. Device is not connected.
Close and come back in.
Do you want to do that?
Let me try that.
Yeah, StreamYard can be a little bit tricky sometimes.
Yeah, we haven't had this problem before.
Yeah, we always have different problems. Right?
Yeah, frequently it's a local thing. Person has a problem with his camera or something like that. Like Nick has been having trouble with his camera, but it seems to be working today. But this does seem to be a StreamYard connection problem.
Yeah, maybe if we can just get him back, since we really only need his audio.
Yeah, you're right. You're right.
But that'd be interesting to hear what he'd have to say about electrodynamics.
Well, that's right. That's right. And
okay,
here we are. And I think we have you in video as well, because we were going to we were going to give up, David.
All right, you can see me now, right?
We just accept your audio, but we have you now both. And,
okay, well, let's get rolling here. Let me.
Yeah, I'm going to hand over to you. May I just? I was going to say this to you in private, and I'm sorry to broadcast it now, but am I correct in pronouncing your surname Bauer, or should it be Bauer?
Bauer. It's not like the German farmer. It's B-O-W. It's not B-A-U-E-R. It's Bauer. B-O-W-E-R. It's
Well,
English.
B-O-W is Bow, and C-O-W in my name is Cow. I'm Cowan. Not
Okay,
Cowan.
Cowan.
People frequently mix that up. So,
well, I'm going to have some things to say about pronunciation. Can you put my slides up? I sent and use the new version,
okay,
please.
I can do that if you wish. You can do it also, but I'll endeavor to do it now. Now let me see. I'll present.
I don't want to touch anything on the screen.
You may have to give me a cue as to when you want to change. That's the only thing.
Okay, that's fine.
I'll put up slides from my computer. Let me see now.
Use the new version, please. I just sent it to you.
Yeah, I got that. Now, what's happening? My internet connection seems very slow today. It actually gave me a warning. I'll have to try that again. Upload file. Okay. Slides. I want the new one, not the old one. New. It's just a bit slow today.
While you're getting the slides ready, can I go ahead and start?
If you wish, if you don't need the slides, it's up to you.
Well, I mean, we're wasting time here.
Yeah, I know, and you need the time. Well, do start by all means. Then
okay. I just want to. I want to find out if Professor Assis is here. I've had a lot of interaction.
No, he's not in the green room.
Okay. Anyway, I would like the audience to actively participate because I want some input. I'm going to try to pronounce the name of Ampere correctly. Likewise, there's a lot of French names. Poincaré is spelled Poincaré, not Poincaré. Liouville. I want to say that these slides don't represent perfection. Harry Riker one time gave me some advice. I told him I want to become the world's leading expert on. Said pick one topic, which is against my nature. But I found that just picking this one topic, Newtonian electrodynamics, is just overwhelming. So even one topic can be overwhelming. So the references I use. Graneau and Graneau, Newtonian Electrodynamics. It's a book. Peter Graneau's paper, Ampere tension and electric conductors. Several papers and articles I've included as addendum to these slides. So I also have you gotten the slides?
Can you see the slides now, David?
Oh, you've got the slides up?
I've got the slides up. Can you see those?
I'm using my own. I'm using my own separate slides.
The first page, Newtonian Electrodynamics. Some people may wish to maximize this, by the way, by clicking the bottom little geometric shape in the bottom right-hand corner of their screen.
Okay, go to the next slide, please.
Go to the next slide.
It's just a title. Go to the next slide. So these are the references I'm using. Next slide, please. I've included, if people want a copy, a PDF of these slides, you can ask Neal. Ask Ewan Cowan. Abbreviations I use. This is self-explanatory. I'm big into abbreviations. I don't like to write things out, but I use ESR for Einstein special relativity and EGR for Einstein general relativity, etc. I think that's self-explanatory. This little thing, ME plus, I'll explain that later. Next slide, please. So this is from the back of the book. The back of book. Newtonian Electrodynamics deals with 19th century electromagnetism. Describes a series of important experiments. Cannot be explained by and analyzed with the modern relativistic electrodynamics of the 20th century. So Coulomb, Ampere, Neumann, and Kirchhoff were used from 1750 to 1900. And he talks about exploding wires, railguns, electromagnetic accelerators, jet propulsion, etc. And next slide, please. So I just want to digress. You know, the way my mind works, I tend to make things complicated before I make things simple. I don't know if any other people's minds work the same way, but I try to make things really complicated and simple. So I think about Newtonian electrodynamics leads me to think about Galilean electromagnetism. And Galilean electromagnetism is consistent with Galilean invariance, useful for describing electromagnetic fields at non-relativistic speeds. Mathematical equations are simpler. So I found some engineering textbooks that tend to divide things up into magnetic realms and electric realms, quasi-static and dynamic approximation. So it might correspond to this kind of stuff, Galilean electrodynamics. Next slide, please. So as everyone, I just want to, I'm going to ask a question, so I want people to think about this really hard. So Galilean transformation relates events, which are points in space at a certain time, in two frames traveling with constant velocity with respect to each other. So there's a Galilean transformation between S and S prime, inverse Galilean transformation between S prime and S, and I've written them out here. So let me ask you a question, a very important question. Can fields be transformed with a Galilean transformation? So in other words, you have something like this, a force F sub x prime equal F of x minus V sub t. How many people say yes? How many people say no? Get your clickers ready. Think about it. Does anyone want to input? Next slide. I say no because fields vary as forces and forces vary as accelerations. Accelerations are not affected by relative velocity. So consider dropping a pebble from a tall building. So we have two frames. One is affixed to the building. One is affixed to an elevator, either moving 10 meters per second up or down. They're going to both measure the same acceleration, right? So how can you transform the force field using a Galilean transformation? Another problem with transforming fields, in my opinion, at least in the instantaneous action at distance limit, there's an asymmetry between the source charges and the test charge test charges. This is always implicit whenever you define fields. The source charge is large, the test charge is small. Now think about this very carefully. Assuming instantaneous action at a distance and moving from point A to point B, test charge will experience the same change in force regardless of how fast the change in position occurs. Since all movement and velocities are relative, this means that if the test charge remains at point A, but the source charge moves from its original location by the vector B minus A, no matter how fast, the test charge will experience the same change in force. Does everyone get that? This means that forces, especially the magnetic forces, cannot be generated by charge movement. Note, consideration of retardation effects may invalidate this line of reasoning. Did everyone catch that? Nick Percival, do you agree with that? Next slide, please. So I'm very wary about transforming fields with either a Galilean transformation or a Lorentz transformation. Seminal paper on Galilean electrodynamics is due to Belloc and Levy-LeBlanc. Hope I'm pronouncing it correctly. Start by assuming correctness of Einstein's special relativity. State there are two regimes in which a corresponding Galilean transformation can be derived: magnetic regime, electric regime. One corresponds to time-like separations and the other corresponds to space-like separations in the four vectors. So then they merge the two regimes to get a general theory. At one time, I thought their two regimes might explain cat theory D, where he says there's no such thing as charge moving, because one of the regimes has no charge in it. So I'm going to investigate that in the future. Recent developments in theory see Rousseau, 40 years of Galilean electromagnetism. Interestingly, they make a lot of really neat conclusions. Okay, next slide. What is Neo-Newtonian electrodynamics? Again, I'm making things complicated. Our esteemed colleague, Dennis Allen, wrote this paper, Can Newtonian Electrodynamics of Professors Peter and Neal Graneau. He goes to revisit the Lathwaite gyroscope thing where it appears to be lighter. And I reproduced my Galilean or my talk on gyroscopes at the very end of this as a PDF, and I added some additional comments if you want to revisit that. Next slide, please. Back to Newtonian electrodynamics. Okay, we've made things complicated. Let's make it simple again. Here's Maxwell's equations in free space and conventional vector analysis. Okay, everyone should recognize those. Next slide, please. Question, do the equations below, i.e. Maxwell's equations, essentially summarize, encapsulate, encompass all of contemporary EM theory as accepted by the majority of scientists and engineers around the world? So I want you to get your clickers ready and give me a yes or no answer. How many people believe that these equations encapsulate, I mean, for most of the world, for the non-descending people, these equations encapsulate contemporary EM theory? Does everyone say yes? Next slide, please. I say no, because the equations almost do this, but what is missing is a force equation. The missing equation is the Lorentz force law. Lorentz force law, F equals QE plus V cross B. I propose that we call the four Maxwell's equations plus the Lorentz force law the augmented Maxwell equations and designate them as ME plus using a plus sign. The augmented Maxwell equations, ME plus, essentially encompass all of the, I got this as a quote from the internet. The augmented Maxwell equations, i.e. ME plus, essentially encompass all of contemporary EM theory as espoused, embraced by the vast majority of contemporary physicists and engineers and chemists, biologists, philosophers, and historians of science, etc. So there you have it. Okay, next slide. Okay, what is the origin of each of the equations in the augmented Maxwell equations? Well, Gauss's law of Coulomb force for electric charge, Gauss's law of Coulomb force for magnetic charge, no magnetic monopoles, Faraday law of induction, Maxwell Ampere law, Lorentz force law. That's the origin of these things. That's their name. Next slide. Okay, next slide. I'm not even going to mention this. It's kind of elementary. Next slide, please. So far. Next slide, please. Lorentz force law is another version of the law of Grassman. So now I'm going to talk about the Lorentz force law. Lorentz force law is another version of the law of Grassman with input from Biot-Savart. Grassman first proposed his law in 1845. It is unsymmetrical and has to be stated using two equations. So the force on M due to N and the force on M due to M. So you have a triple cross product there. Next slide. So again, remember what I said about whenever you have a field, you have to think about the asymmetry. You have to have a source and a test charge. So here, I'm going to just focus on one and recast it using a source and a test charge. And I'm showing how you can get the Lorentz force law from this. Delta F on the test charge is equal to Q times the velocity of the test charge times the magnetic field. Does everyone see that? Where the magnetic, it's pretty obvious how I define the magnetic field, infinitesimal magnetic field. So this is how you get the Lorentz force law from the law of Grassman, which has morphed into the law of Biot-Savart. So Biot and Savart did some measurements on the magnetic field, and somehow their name got affixed to the law of Grassman. Okay. Next slide. So Lorentz force law, continued comparison of the Ampere and Grassman force laws. I haven't talked about the Ampere law yet, but we have these three angles. We're going to have epsilon, alpha, and beta. Epsilon, this is very confusing to me for a long time, especially going through the derivations. I got all these angles confused, but epsilon is the angle between the two current elements. Alpha is the angle between one current element and the line that connects them, and beta is the current angle, is the angle between the other current element and the line that connects them. Does everyone have that in their mind? Let's just take 10 seconds to put that in your mind, okay? 1001, 1002. All right, everyone's got that firmly in their mind, right? So this is just showing you how the angles of the Grassman law are related to the angles of the Ampere force law. Next slide. So the $700,000 question. Does everyone know what the $700,000 question is? Well, back in 1965, it used to be $64,000, but now due to inflation, it's the $700,000 question. Why did Grassman develop and advocate his force law? Well, so now I'm going to kind of just read the slides instead of kind of summarizing, because this is important. It's rather surprising to find that Grassman had enunciated his laws 20 years before Maxwell wrote his field equations, but at that time only Faraday was speaking of magnetic flux. And I copied this right from Graneau. Grassman was a mathematics teacher at a German high school. Actually, it should be a German gymnasium, I believe, because maybe it was a high school. You know the difference? German high schools are actually universities. German gymnasiums are our high schools. But anyway, so I don't know whether he was teaching at a university or a high school. Grassman's great achievement as a mathematician was the introduction of vector calculus. There's some suspicion that he proposes new electrodynamics mainly in order to have a good application for vectors. He certainly achieved this with his equation above. The Lorentz force expression made its appearance in the 1890s, 50 years after Grassman's paper. Lorentz was led to his equation by his theory of electrons. On Grassman's own authority, his investigation was prompted by two objections to Ampere's force law. His first objection, he considered attraction and repulsion to be an arbitrary assumption, and also could see no reason why current elements should behave like gravitating and charged particles, which were scalar quantities, while current elements were vectors. You know, at first when I was studying this Ampere current law, or Ampere force law, and he expressed everything in terms of current elements, I said, how in the world can you tease out the effect of a current and associate it to a current element? Then it dawned on me that this current element, like I sub n d sub ln, is essentially just, you know, a charge, a density of charge times a velocity. So I d sub m, or q sub m d sub m, is similar to q sub n v sub m. Anyway, I still don't understand how he teased out all the effects, but he was very ingenious, and I think we've lost some of this experimental skill due to the internet and our constant bombardment with social media, et cetera, et cetera. Anyway, next slide. So he was also turned off by this complicated, arrangement of all these cosines, and found that there was that it went to zero when you had certain orientations. So next slide. Next slide, please. So this is kind of a diagram showing how if you have two current elements and you put them at different angles, how the force will be related. So you can see when you have the two current elements parallel and on a line, there's going to be a certain amount of repulsion, right? Then that goes down to zero. Is everyone with me? As you turn the second or the test current element to 30 degrees, it's going to be almost zero. Then we turn it back to 90 degrees, it's going to be larger again. And when you turn it to 30 plus 90, it's 120. It goes almost to zero, and back to 180, it's large again. So in fact, I'm going to read another little quote from Graneau. It said, when two current elements lie on the same straight streamline, we have cosine epsilon equal cosine alpha equals cosine beta equals 1, right? Epsilon is 0 because they're on the same line. The angle between them is 0. And the alpha is 0 and the beta is 0, right? So they're all 0, and so cosine of 0 is 1. So the force becomes like a Newtonian gravitational thing. I sub m times I sub n times dn over r squared. So it becomes just like two masses. Well, Grassman really didn't like this complicated arrangement. So that's another reason why he came up with his laws. Is everyone with me so far? Next slide, please. So I'm going to talk about Ampere's law in just a minute, but let's talk a little bit more about electromagnetic induction. Finding mathematical laws capable of quantifying Faraday's 1831 discovery of electromagnetic induction took much longer than Ampere's deduction of a force law from the discovery of electromagnetism. So Neumann investigated induction and divided these forces up into a PMF, or pondered motive force, given light by the Ampere force law, and EMF, or electromotive force, which move the electrons. So there's two guys in Leipzig, Germany, Fechner and Webner, and they felt that the EMF and PMF forces were essentially the same thing. And so Fechner instigated Weber to search for a force law to explain EMF and PMF. And Weber came up with this really interesting force law. Next slide, please. So this is his force law. And Professor Assis has done a huge amount of work on this. So it has the terms. The first term relates to the Coulomb law, instantaneous action and difference. The second one has to do with Ampere force law, and the third one has to do with EMF, or induction. Next slide. So before we go on to Ampere's force law, which is the basis of Newtonian electrodynamics, let's just talk about what I call forgotten EM force laws. So we do have Ampere force law, which I haven't really talked about yet. But it's probably been forgotten because it cannot be incorporated into a field formulation, i.e. the field formulation of Maxwell. As I said before, it's often confused with the Ampere current law, which is another attempt at obfuscation. The Grassman force law. Grassman force law achieved new life as a reincarnated Biot-Savart law. Then Weber force law. Weber's law seems to be a law that encompasses both Ampere's force law, which governs PMF, and the laws of EMF. JPW, by the way, does everyone know who I'm talking about with JPW? Raise your hand so I can't see you, but JPW stands for another person I study a lot, is James. Help me with this, Dennis Allen. James Powell Wesley claims that Weber's law can resolve the paradox of unipolar induction, i.e. Faraday's paradox. Then this guy named Walter Ritz improved Weber's force law. Next slide, please. We have the Einstein-Laub force law, which is advocated by Mansour Apur. Have you heard of Mansourpour? He was the author of Mansourpour's paradox. He's written a lot of articles on hidden momentum. Hidden momentum is this thing, my understanding, and I don't know a lot about it, but it's this development, this concept, which has been developed to try to explain the reason or the effect that Lorentz force law does not respect conservation of momentum. So they have to invent all this, find all this hidden momentum. Then we have the Abraham-Lorentz force and the Abraham-Lorentz direct force, which is a modification of the Lorentz force to take into account the radiation reaction. So whenever you have the Lorentz force acting on a charge and it moves, it's going to emit radiation. So these guys have tried to take into account the radiation reaction. Next slide, please. Here again is the so now I'm going to transition to the force law of André Marie Ampère. Again, we see the epsilon angle is the angle between the two current elements. Alpha is the angle between one current element and the line connecting to, and beta is the angle between the second current element and the line connecting them. Okay, next slide. Oh, by the way, this slide does show the Ampère force law. Okay, it acts between the midpoints of the current elements. Here, this is just another maybe clearer picture of the angles. Next slide, please. Now, I want another digression. As I was sleeping on my bed the other day, I was obviously in contact with the sheets and the mattress immediately underneath me, and I got to thinking, why am I not held to this bed with an infinite force? After all, the distance between me and the bed is essentially zero. Have you ever thought about that? Things like that? Maybe I think too much. You know, here I'm trying to sleep and I'm thinking about the inverse square law. Don't inverse square type forces lead to infinite forces as r goes to zero? Consider Newton's law of gravity. Consider two spheres of radius r and density rho mass proportional r cubed in contact at the surfaces. And I was going to draw some two spheres, but I didn't have time. Fortunately, the limit as you take the radius r of the sphere, and you're considering these spheres to be uniformly filled with mass of density rho, the limit as r goes to zero also goes to zero. So that put my mind at ease, you know, explained why I'm not stuck to my bed with an infinite force. Next slide. So I didn't have time to really develop this, but then you have to start thinking, what if you have a whole box filled with these little spheres? And then you have to sum up all the vector forces. And I'm confident in that case, you also, do you understand what I'm saying? All right. You have a box filled with these spheres of radius r, and then you take the limit as r goes to zero. And I think you'll agree with me that you'll again get a zero, not an infinite force between two boxes. Well, then you have to worry about Ampère's force law. Do you get these infinite type forces when you start thinking about these infinitesimally small current elements? And this is extremely important when you start thinking about modeling, doing computer modeling of all these little current elements, which I'm not going to have time to talk about. Next slide, please. Again, oh yeah. The current, I'm trying to be funny here, paradigm for interaction of current carrying wire is the source wire sets up a magnetic field. The test wire responds to the magnetic field caused by the source wire. And this situation is similar to the use of source and test charges in defining the electric field. Newton's third law is violated. Now, controversies exist over whether current elements can be used or whether a complete circuit must be used in analysis. And then we have the controversy of hidden momentum. I think the consensus is that, I believe the consensus is that when you talk about two complete circuits, the Ampere force law and the Lorentz force law will give you the same force between these two circuits. However, the distribution of forces will be different between the two laws. Does that make sense? This is my general understanding of comparison of these two laws. Anyone want to make a comment? I'm not looking at the chat, so I don't know whether people are agreeing or not. Next slide, please. This hidden momentum controversy.
David, if I may quickly interject, I'm trying to keep an eye on the chat. That's why I'm not very immediate in changing the slides. But people are generally not replying to your questions, probably because you're not giving them enough time. But I'll let you know if they are.
Okay. All right, next slide, please. Does everyone know what I mean by ME plus here? Oh, this is an interesting little slide here. I want to talk about this. How the Weber and Ampere force laws explain the magnetic force continued. Nobel laureate Edward M. Purcell, by the way, has everyone ever heard of him? Has everyone heard of him before? He was very important in my field of medical physics because he was one of the two inventors, or I don't know whether he invented MRI or did the engineering that allowed MRI scanners. But anyway, he got a Nobel Prize for MR resonance, nuclear magnetic resonance. He gave an explanation for the existence and action of the magnetic field generated by a long straight conductor in terms of the length contraction of Einstein's special relativity. I put magnetic field in quotes because some people do not believe in its existence. Like I know Professor Assis does not believe in the magnetic field, and I tend not to believe in it. I think these electric and magnetic fields are just computational tools. But I believe Purcell's explanation of the magnetic force is an error. J.P. Wesley has shown how the Weber force law can explain the effective action of the magnetic field. And in fact, I've affixed a paper at the end of the talk, his paper on extending the Weber force law to a field. If the Weber force law can explain the action of the magnetic field, then the length contraction of Einstein's special relativity is redundant and obfuscatory or confusing. Does everyone agree with that? What does the chat say? They agree? Okay. Next slide, please. Ampere's force law, pros and cons. Well, first of all, we don't know whether it's really the correct law. I tend to think it is, but I found one paper that kind of doesn't agree. It respects the third law of motion, momentum is concerned. The con with it is you cannot make a field version of this law, as with the Lorentz law. So that's some of the pros and cons of the Ampere force law. Next slide, please. Yeah, this is what I was saying about the electrodynamic force law controversy by the two Graneaus. Cavalieri has attempted to resolve the electromagnetic force law controversy, which is whether the two laws are identical, and if so, when are they identical for just current elements or for entire entire circuits? I mean, circuit elements or entire circuits. This attempt to prove the validity of either the Ampere or Lorentz force law by theory and experiment has revealed only that the two are equivalent when predicting the force on part of a circuit due to the current in this complete circuit. However, in our analysis of internal stresses, only Ampere's force law agrees with the experiment. Now, unfortunately, I'm not going to get into a lot of the experiments. I did find that for everyone who says, it seems like for everyone who says that the Ampere force law is correct, you can find someone else who says the Ampere force law is not correct. The establishment has a vested interest in protecting the Lorentz force law. I tend to agree the Ampere force law is correct. Next slide, please. I think that's a duplicate somehow. Go ahead. Next slide, please. So is the Ampere's force law correct? Graneau and Graneau offer the following as proof of the correctness of the Ampere force law. experimental evidence for longitudinal ampere forces, ruptures of wires, mercury jets, theory of rail guns, arc explosions, developments in nuclear fusion and cold fusion. So they give these as evidence that they're correct, that the ampere force law is correct. Next slide rather. Wesley and Hermann Hartel offered following as proof of the correctness of the ampere force law. Mironov and ampere motor. I haven't had time or haven't taken time to study these, but Wesley and Hartel both discuss these. I'm not even sure whether these motors are the same thing. Probably are, but haven't read these papers. Resolution of the paradox of unipolar induction. Professor Keene gave me a really, really neat argument showing that triboelectricity, or the static electricity generation, can explain unipolar induction, the paradox. And I said, "Wow, Professor Keene, that's really, really neat." And I believe you, and I still do believe it, But I'm going to read these papers by Wesley and Hartel, saying that ampere force law can resolve the paradox of unipolar induction. Okay, next slide. I'm going to let you read that. I'm going to skip over that. Basically, he said that Lorentz, this is a question. It's another $64,000 or $700,000 question. The first $700,000 question was, why did Grassman develop his force law, which doesn't respect Newton's third law? And the second $700,000 question is, why did Lorentz abandon ampere force law and use the Grassman law on his stepping stone to develop his force law? Well, it has something to do with the force on electrons in gases. I don't know enough to comment on this, but Lorentz certainly introduced a lot of controversy when he went ahead and leapfrogged over ampere and used a force law that kind of mirrored Grassman's law. Any questions or comments on that? Let me see if I can find that in that. Maybe it's in a different thing. All right, next slide. Now, this article, I did read it to the end, and I tried to understand it. I can't understand things unless I can duplicate them, typically. So this gentleman did a lot of computer calculations, Paul Moisides, and he used some CERN routines, some CERN computers in 1989. I think the computers back then were pretty powerful, even for 1989. And he modeled these current elements and integrated them all. And his conclusion was that that ampere and Lorentz gave the same results. He says the results show that, taking into account the statistical and systematic errors of the numerical method, the ampere law is in complete agreement with the experiment, in contraindication to other experiments which state the opposite. Well, I guess he's just saying ampere gives correct results, but I think in another place in this result, he says, okay, yeah, let me quote something he says in this paper. He says, the present paper, along with the experimental one. So I guess he did an experiment where he measured the force, and then he did a computer simulation also. He said the present paper, along with the experimental one and the theoretical one of Biot-Savart Lorentz, proves that for the first time, even if they refer to a specific configuration that the two laws are equivalent between parts belonging to the same circuit and also in agreement with the experiment. We use sixfold integrals to overcome the singularities and infinities involved both in the Ampere and Biot-Savart-Lorentz law in this case. So there you have it from this gentleman who did both experiments and computer simulations. Next. However, I'm very, very suspicious of computer simulations. Very skeptical. Garbage in, garbage out. In other words, does anyone else share skepticism with computer simulations? Go ahead. Next slide, please.
Just a very quick point, not about my skepticism about computer simulations, which of course I share, but it might help just clarify that what you're referring to as the Grassman law is normally the one which is quoted as the Biot-Savart law. It's the same thing. It probably should be attributed to Grassman because he might have done some earlier work. But I think in normal academic,
you could call it a lot of different things. You could call it the Grassman law. You could call it the Grassman-Biot-Savart law. You could call it the Grassman-Biot-Savart-Lorentz law. I mean, there's like several different iterations of what you could call it, but they're all basically the same law, I think.
Okay, because the Lorentz force law basically is equivalent to that. It flows from it. You know,
yeah, I showed that in a previous slide, how you can derive the Lorentz force law from the Grassman law.
Okay, thank you.
Yeah. Next slide, please. How much time do we have? Just 1 hour? All right. I'm going to wind it up here.
The tradition is to have an hour. However, that's 50-50 split between presentation and Q&A. But it's completely up to the speaker. If you want to take 1 hour, 15 minutes, even 1 hour and a half, that's fine. It's really up to you. But we normally say about an hour. But if you want to take a little more, that's quite all right.
Let me just run through these last slides fairly quickly. I wrote down a bunch of possible topics for future lectures. So anyone who gets a PDF of these slides can find this. Why don't you just go next slide, please. Part 2 of some different topics. Part 3, next slide. Next slide. Notice I put Mach's principle, kinematic relativity of Milne, four-dimensional Stokes and divergence theorem, time-dependent Helmholtz decomposition theorem, Lewin voltage paradox. Next slide, please. I'd like to talk about Harry Ricker's filaments in space. I never got around to that. Our black holes. I mean, there's just a load of different topics. Next slide. Next slide. Bridgman says there's two types of EMF. There's a huge controversy about whether energy can be localized. There's tremendous paradoxes of the Poynting theorem. Hans Schantz has some really interesting ideas about EM theory. Classical models of the electron, you had all these different models of the electron. You have this huge, what I call fuzzy logic about mass and energy. Next slide. What makes a theory understandable, explanatory? This is a huge topic. What makes a theory good? What makes a theory offer an explanation of something? The whole argument of Einstein, the qualitative EM theory of Hermann Hertel, renormalization, Maxwell's equations without the displacement current term, is the Higgs mechanism an error? Next slide, please. Bell's theorem in overcomplete sets. Davidov's proof that electric magnetic fields do not commute. Hydrogen atom with Weber force law. 6 spiritual laws, which is something different, but something I like to talk about. To paraphrase Groucho Marx, those are my suggested future lecture topics. If you don't like those, I have others. So a lot of things we can talk about. Next slide. I want to end with my basic approach to physics and science. How many people have heard of Immanuel Kant's antimonies? I'm not looking at the chat. Has anyone heard about these antimonies? Immanuel Kant was
I'd
a
say
famous
yes,
philosopher.
yes, for me.
How many people do you think know about these? Half, 90%? Well, there was Ian, I'm sure you've heard of William Hamilton, the Scottish philosopher.
Yes, not to be confused with William Hamilton, the Irish mathematician.
No, don't confuse William Hamilton, the Scottish, I believe, philosopher, with William Hamilton, the Irish polymath. William Hamilton was a philosopher in the Scottish tradition. He came up with this philosophy of the conditioned. Basically, he says that the Creator has placed limitations on our thought processes. Basically, the way I interpret what he's saying is that just as a bird cannot overcome the limitations of the atmosphere and fly to the moon, so we as humans cannot overcome the limitations which the Creator has placed on our human thought processes. For example, there is no way with these limitations placed on the human mind that we can resolve these antimonies that Kant has brought up. For example, is space limited or is it bounded? Well, either one of these limitations is just untenable to the human mind. Did time begin, or can you go backwards in time forever? The human mind cannot. I mean, both ideas are untenable. We cannot comprehend which is true. So the philosophy of condition, William Hamilton says to think is to condition. Mansell, a theologian, developed this further in The Limits of Religious Thought, and he made an interesting quote, building on the work of William Hamilton. He said, "This submission of reason to the authority of revelation, i.e. the Bible, is not, of course, a solution of our rational difficulties. It is only a belief notwithstanding those difficulties and a trust that there is a solution, though we may be unable to find it. And thus it is that an examination of the limits of religious thought leads us ultimately to rest not on reason but on faith. This assumption appeals not to our knowledge but to our ignorance and shows that our intellectual trial in this life is analogous to our moral trial, that as there are real temptations to sin, which nevertheless do not abrogate the duty of right conduct, so there are real temptations to doubt, which nevertheless do not abrogate the duty of belief." So I just thought that was a really interesting quote, especially for me as a Christian and someone who believes in the Bible and a supernatural creator. So with that, I want to end my talk. As I said, the PDF, which I sent to you, has a whole bunch of other stuff. Could you briefly just scroll through the other stuff that it has? Here's an article where the guy says that railgun recoil, that he does not agree with Ampere law being superior to Lorentz force law. Okay, scroll. Just scroll quickly. Quickly scroll. Scroll. That's just the end of it. Scroll. So here's a famous article, Weber Electrodynamics extended to include radiation. He talks a lot about the Weber force law, how you can derive the magnetic field and blah, blah, blah. It's very, very interesting. This is an article. I tried to work through all the math and I got stuck, and I wrote to a bunch of people. And Dennis Allen in particular says, the math wasn't quite right in this, but if you look at the books he wrote later in life, that it corrects the math. Scroll through this, please. Keep scrolling. Scroll. Now, here's an article about the Marinoff motor that Wesley wrote, saying he says it cannot be explained by anything but the Ampere force law. Scroll. And there's an article about Hermann Hertel, which he claims the same thing. The Ampere force law is necessary to explain this motor. Scroll, please. Here's a reprise on my gyroscope lecture, if you want to just quickly scroll through that. Do you remember I gave this lecture probably about 6 months, a year ago? I don't remember. Scroll. I added some comments at the end. Scroll, keep scrolling. And then we'll be complete. Keep scrolling to the very last slide. I thought a little bit more about this. This is okay. Go back to the previous slide. To see if there's really an anti-gravity effect, perform the lifting with a person lifting the spinning gyroscope standing on a scale. Okay. These are additional ideas, I thought. The Journal of the Physics Teacher has 2 articles purporting to debunk the Lathwaite video. I've attached them. EJP article by Provatides entitled Force Precession of Gyroscope and its application to Lathwaite's engine. Lathwaite's engine is an engine supposedly providing thrust. He talks about this. And finally, what makes a non-spinning gyro so hard to lift? Counterbalancing the torques tending to make it fall over makes it very difficult to lift up. In other words, if you were just to lift a bowling ball, spherical bowling ball, 40-pound bowling ball, it'd be fairly, I mean, I do a lot of weightlifting, at least in the past, so it's not that difficult for me to lift up a bowling ball like that. But when you start putting a rod on it and introducing torques, that's going to really complicate things, because you have to hold it straight up, and then you've got torque. You have to counteract the torque. Do you understand what I'm saying? Now, when you rev it up and you're spinning the gyroscope, the torque is counteracted by the spinning of the wheel. So you can stand there and just hold it level with 40 pounds of force, and you can raise it over your head with that 40 pounds, So anyway, plus what I think when he tried to drag it around, he added a little kinetic energy to it, which he converted into potential energy as he raised it. Do you understand what I'm saying? Anyway, the last 2 articles, you can scroll. These are from the physics teacher talking more about the spinning disk. Debunking a video. I haven't read this. One of his students tried to debunk this video. And if you have trouble reading it in the PDF, you can always expand it, go up to a different magnification, and it's easier to read. Okay, so that's the sum total of my talk. Do you want to open up for some questions? Not that I'm an expert on this subject.
Well, thank you very much for that stimulating exposition. There was a lot of material there. I knew that when you sent me the slides, and I was wondering how you'd be able to get through it all. But you did generally. And I, as you said at the beginning, if anybody wants more information, he can contact me, and we can supply the further information, the PDFs if necessary. So maybe just a couple of comments and maybe a question or two. We have a number of people in the green room, and I'll be bringing them up. And I see that Professor Assis, whom you invited on my behalf, has joined the green room. So we'll bring him up presently as well. We have actually, now that I've brought your slides down, I think we're all right. We haven't overloaded the green room. So, yes, you covered the difference between maybe the conventional Grassman Biot-Savart way of thinking and the Ampere thinking with regard to force laws, and the contention which, say, J.P. Wesley might have emphasized, that Newton's third law is not satisfied by the former, but by the latter. And that the Lorentz force law, as we said, is basically almost a corollary of the Grassman type system. So perhaps if Wesley is correct, that doesn't comply with the third law. And therefore, you're getting into the area of sort of perpetual motion machines. But maybe before handing it over, I just have one question. You may wish to comment on some of that as well. What my question was, you didn't mention, I think, the possibility of obviating the non-invariance of Maxwell's equations and the electrodynamic equations under Galilean transformations, in other words, using Newtonian dynamics, by using a total time derivative, a convective derivative, rather than a mere time partial derivative. So I'm just wondering, what you might think of those points.
So you mentioned the convective or the total derivative, and what was your question? You said
my question is that well, let's look at it this way. Here's my hypothesis, and I wonder what you think of it. Galileo used some very strong arguments as to why these intuitive transformations would work, and in particular, if you had a vessel, for example, moving at a constant velocity, you would not know that unless you had a frame of reference, such as the shore, because you could do any mechanical experiments and they would give the same results. Now, Maxwell's equations obviously appear to be quite successful, and then maybe predicting a sort of electromagnetic radiation and so on. But there seemed to be a problem, when you were converting from one frame to the other. So one way of looking at the derivation of the Lorentz transformations, or maybe a variation of the earlier Voigt transformations, would be to say what transformations would be needed to make Maxwell's equations in the form that he wrote them invariant. And you find that you need these extra factors, gamma factors and all. You need the Lorentz transformations.
Right.
Einstein, in his 1905 paper, attempted to generalize that by saying, they apply to everything. They apply to ordinary dynamics. And here's the explanation. And if we take the speed of light to be constant, independent, not only of the speed of the source, as in his second postulate, but of the speed of the observer, will you get the Lorentz transformations? But Hertz then came along, not very long later, and he...
Hertz, you said? Hertz?
Heinrich Hertz, yes.
Hertz, okay, yeah.
The experimenter who actually verified the electromagnetic radiation, and that sometimes has eclipsed his proficiency as a theoretician, because he, as far as I can see, was the first to introduce this concept that if you have a sort of a convective derivative, where you have the partial derivative augmented by the dot product of any velocity and the nabla or del operator.
Right.
So this is used in fluid dynamics. It's
right,
general.
Right.
Yeah. So
yeah,
if
you have two. In fluid dynamics, you have two different competing versions of the convective derivative. You have the Euler derivative and what's the other one? Lagrange.
Yeah. That's just two different ways of looking at it, whether you look at it from the point of view of a fixed element with the fluid flowing by, or you look at it as the history of any particular molecule of the fluid. But I mean, the concept is still the same. It's right, there are two different expressions, the Euler and the Lagrangian. But if we take this concept, and if we do a bit of mathematics, we find, hey presto, the Maxwell equations so modified are invariant. So in other words, wherever you have a partial time derivative in the Maxwell equations, which you've put up, you have it's usually put in form of capital D by dt, which is the convective derivative. So therefore, I say that the Lorentz transformations really applied to certainly to the everyday world are otiose, which just means they're redundant, they're lazy. There's no dynamic aspect for them. They're really a quick fix. They're an adjustment tool. So I'm just wondering, you didn't mention that convective derivative. Have you any views?
Okay, that's an interesting topic you bring up, because about a month or two ago, I remember reading an electrodynamics theory developed by someone. I think he just died, but he used a convective derivative, and he placed the source and the test object on the same footing. Now, who was that? Who was it that just developed it? Phipps? I believe it was Phipps. Does that name ring a bell?
It does. And actually, I've taken the liberty of putting Thomas Phipps' name in the chat to some comment which one of the persons made. So I think you're probably right. He wrote extensively on this subject. You are dead right there, David.
Yeah. Phipps developed a theory which he said was based on Hertz's theory, where he says that not only do you have to see, Einstein just thought about receiving this light signal. That's all he was concerned about at a specific point. But he said you also have to take into consideration the source. And so he was using the convective derivative. I'll have to revisit that. It was Phipps. I remember it was Phipps. Phipps and Hertz. Yeah.
Yeah. Phipps has written extensively on this, indeed.
Well, thank you for bringing that up. Thank you for bringing that up.
Okay, no, thanks very much for your comment. I'll just reply to a comment. And okay, so what I'm proposing to do now is,
and that excuse me, one other thing that has that's also related to Walter Ritz's work with ballistic theory.
Yeah,
well, Ritz said you had
related, but Ritz, in contradistinction, talked about the speed of the source having an effect upon the speed of the radiation, which in its just bald form seems to be untrue, because it's like if you take a water wave which is formed. Well, the speed of the water traveling through space, let's say absolute space, does not affect the speed of the wave. And similarly,
yeah, but it certainly affects the speed of a bullet. I mean, if you fire a bullet out of a handgun, it's the speed of the handgun is going to affect the speed of the bullet.
It certainly affects it in the case of a cannon or a bullet. That's true. So the fact is, or the question is, does the same thing, ballistic principle, apply to waves in a medium? And Ritz said yes. Well, I say no anyway, and it appears to be against experimentation. But
if you look at the first two topics on my suggested future topics is related to Ritz, his disagreement on Einstein about the ballistic theory, and also his disagreement about the asymmetry of radiation. The asymmetry of radiation. So maybe we could talk about that.
Well, I think he's wrong in the latter, but actually, if you take boldly the second postulate, where
Ritz was a fairly smart guy, I mean, Ritz was a pretty smart guy. If you're going to say that you disagree with him, you better have read all his papers and everything.
Well, the general public say that the most brilliant mind in the last century was Einstein, so you daren't disagree with him either. So,
it wasn't Einstein who was smart; it was his wife, Mileva.
Well, maybe so. Actually, I think there is some experimentation. We could talk about this another time. And there was a company just across the road from where the Titanic was built in Belfast called the Sirocco Works. They were producing cooling equipment for drying equipment for tea, which is imported from India. But they actually developed the first air conditioning system in the world. And they were using centrifugal fans, which were actually put on the Titanic and her sister ships as well. But the inventor there was a very hands-on man. Davidson was his name. And he said, 1 ounce of fact is worth a ton of theory. So,
let me just give you a little trivia question. Maybe we're getting toward the end, but let me give you a little trivia question.
In the green room, an opportunity to go in, so I'll shut up after this. But go ahead, David.
One little trivia question. I'm a medical physicist and a radiation oncologist, and I used to go around to different hospitals and test MRI machines, CT scanners, blah blah blah, make sure they're working properly up to standards. And one thing I walk into rooms with technologists and see a CT scanner. It would say GE up there, or maybe Philips. And I said, if history had been a little bit different, and I do this with a Siemens, I'd see a Siemens scanner. Yeah, I'd see a Siemens scanner. And I said, if history had been a little bit different, what name would you see up there instead of Siemens? So think about that a little bit. Is everyone with me? Instead of seeing a Siemens GT, Siemens CT, or a Siemens MRI scanner, what name would you see up there instead of Siemens? It's a trivia question.
Well, it could go back much further. You've frozen again, actually, David. There's a little problem with freezing here, but I think everybody else, sort of online, and the only person to have frozen is David. And I'm not sure if he's aware of it, actually. What happened on a previous occasion is I just brought somebody up. Well, I think what we'll do now, because I think he'll come back in a moment from past experience, and we have half an hour left. Well, we have 30, more than that, 40 minutes left. So if anybody in the green room has anything urgent, he can wave his hand and I'll bring him up. But if he doesn't do that, I'll go through you all sequentially, because you probably know my style. I feel that anybody in the green room really is invited to talk. So Denny has actually taken my offer, and I'm going to put Denny up now. So Denny, please fire away.
The Lorentz law of force has been generalized by Wesley in his last book, his last solo book, in equation 5.1, first equation of chapter 5. And there's an extra term on the right, which he didn't mention until equation 5.24. And this can be interpreted as a generalization of the Lorentz law of force. And so you should realize that when Wesley talks about the Lorentz law of force, he has something different in mind than the average person would do, studied in college, the Lorentz law of force. Wesley's law of force reduces to the Lorentz law in certain cases, but he points out, for example, that if the magnitude of the acceleration of a charged particle is not constant, I'm not talking about the direction, I'm talking about the magnitude is not constant, and the Lorentz force, as usually known, does not conserve energy.
So David, you followed what the point that Denny's making. He was referring to Wesley's book and the particular equations.
Yeah. By the way, thanks for your advice to get those books from Mrs. Wesley's widow. I got both of the books, Advances in Scientific Physics and Advances in or Advanced Physics. I got the two books, and it's on my to-do list, which has about 200,000 things on it. But I do thank you, and there is a controversy about some people criticize the Weber force law, saying that it didn't conserve energy, which is, for someone who believes in the Grassman and Lorentz force law, to criticize the Weber force law for not conserving energy when it doesn't conserve momentum. It's kind of like the pot calling the kettle black.
I wonder, could there be sort of a dichotomy here? Because if you look at the basic equations, perhaps of dynamics or maybe of electrostatics, where you have things like capacitors with CV squared or MV squared in the dynamics case, it appears at first glance not possible simultaneously to conserve energy and momentum. I mean, one has a V in it, the other has a V squared. And frequently in experiments, the conventional physicists say, the excess energy is just given off in sound of a collision or something like that. But
I found a most remarkable paper, extremely remarkable paper, relating to the relationship between conservation of energy and conservation of momentum. If I can just basically quote it without looking at it, it says that in special relativity, Einstein's special relativity, using the four-vector approach, conservation of energy implies conservation of momentum and vice versa. You know, the logical symbol implies, which is an arrow, a left and right harpoon. If something implies something else, it means they're equivalent, especially if they each implies the other. So in special relativity, conservation of energy implies conservation of momentum. However, in classical physics, conservation of energy, or is it conservation of momentum, implies conservation of kinetic energy, but not conservation of total energy. See if I got that correct. Because did you get that? So there's a dichotomy between the way special relativity operates and the way classical mechanics operates. In special relativity, one implies the other in the 4-vector, whereas in classical mechanics, one doesn't imply the other. So we know that momentum is always conserved. In relativity, momentum is always conserved, energy is always conserved. But in classical mechanics, momentum is always conserved, but energy is not always conserved. For example, if you have an inelastic collision, you're going to conserve momentum, but you're not going to conserve kinetic energy. Some of that kinetic energy is going to be converted into heat. Did I make myself clear as mud?
Heat and sound, yeah.
Clear as mud, huh?
Well,
it's a very subtle but profound difference between Einstein's special relativity and classical mechanics.
Yes, but go ahead.
No, Danny.
The conservation of momentum rules out inertial propulsion, which is known to exist. The Boeing company, for example, uses it to keep their small, low-level satellites in orbit. So conservation of momentum doesn't even hold in classical mechanics.
Say that again?
Boeing aircraft, Boeing's aerospace, whatever they call it, used to have a supervisor in, I believe it was in Washington State, by the name of, what's his name? It'll come to me in a minute. And he, in his laboratory, and I can send you the slides if you like. In his laboratory, they had gyroscopic machines which did not conserve momentum. They had inertial propulsion, which means that you have thrust from within, which you're not supposed to have according to Newton.
Huh.
But they did. And as I say, I'll send you the slides if you're interested.
Yeah, that'd be interesting.
Mike Gamble was his name, Gamble. And he got permission because of an earthquake and some other things that the laboratory was destroyed. He got permission from Boeing to give a talk in 2015 in which he pointed out that Boeing had been using inertial propulsion to keep their low satellites in orbit because otherwise there's eventual orbital decay. And so that proves that even in classical mechanics that momentum is not conserved in general.
Huh. And David, you yourself referred to Lathwaite's experiments, and I think some of the interpretations would be akin to what Denny said, that those are inertially induced systems.
I'll have to look at that. I wasn't aware of that.
Would you like me to send you the slides? Would you like me to
sure.
send you?
Sure.
Okay. I'll do that.
Okay. Well, thanks very much for that. Now, is that all, Denny? I want to. Yeah. Thank you very much for that. I want to get in a moment to the green room. But there's just one question here which has come up, which you might wish to address very quickly. What is your opinion of? He probably means Graneau, water explosion experiments. Are you familiar with that, David?
I haven't studied that. I'm still working full time, believe it or not, and so all this is kind of a little extra hobby that I have on the side, and I don't have an infinite amount of time to study everything.
Well, you've certainly given us an inroad into this very extensive subject and all these papers, which will require a lot of further thought. Now, you have invited Professor Andre Assis, and he's here. Now, I just perhaps take the liberty of bringing him up and saying, you're very, very welcome, Professor Assis. And I'm wondering if you have any comment on what David Bauer has been saying, or indeed any question you wish to pose to him.
In the first place, I'm very thankful, David, for the invitation, Jan Cohen for allowing me to be with all of you.
It's our pleasure. It's our pleasure.
Quite.
Yes. No, I'm just here just to watch and to appreciate what you are doing. So,
well, thank you very much.
Well, thank you very much. And I certainly would refer many of our participants to a lot of your very impressive works, so they could Google some of the information and get some of your papers.
It's good to finally see you face to face.
Yes, same. Can I say?
And indeed also for me, because I've seen some of your publications, but it's lovely meeting people, even if only virtually.
Yes.
In addition to all my investigations of physics, I'm trying to learn Spanish. I have a tutor in Argentina.
Okay.
And I want to use Spanish as a springboard to try to understand German, and then my wife's native language, which is Russian.
Okay.
And then Arabic.
So many languages.
I can't even learn Spanish.
Yes.
And it's more spoken in the
USA
languages, than in this part of the world.
How many languages do you speak, Professor Assis?
Portuguese, my mother tongue, then English, French, German. I can understand Spanish, and so that goes.
That's amazing.
Well, perhaps I shouldn't say this, but I've actually noticed that Portuguese people here in Ireland, they have the best English. They're excellent, perfect. And I was speaking to them, and I said that. I said, some of the Spanish people here, they have an accent, and they're not getting things quite right. You are perfect. They said, we learn English from a very, very early age. That's what they said to me. So anyway, for what it's worth.
I worked with a gentleman from Morocco in Saudi Arabia for 2 years. This gentleman was a Berber. He's a Muslim, but he spoke Arabic. He spoke French, which he learned as a child. So Arabic, French, English, and Berber. His name was Senhu. It's just absolutely amazing, and I can't even speak English properly.
Today, during the lunch, I just met a guy who knows 10 languages: Russian, Spanish, Ukrainian, and German, French, everything. There are some people who are simply incredible.
Well, that's true, and I speak for all English-speaking peoples to say that we are the worst. We expect everybody to speak our language, and we're very bad at other languages. So thank you very much for coming today. And if you want to come back, by the way, just wave your hand, and I'll bring you back.
Okay.
Thanks indeed. Now, so we also. Anybody else? It wasn't Bob. Yeah, I thought Bob did raise his hand. So I'll bring Bob Gray up, because he's done a lot of work on Weber electronics. And in fact, he's given us a presentation or two on the subject, and we've corresponded privately. So any question or comment on David's system, Bob?
Yeah. Hi, David. Thanks so much for the presentation. It sounded a lot like you were going down the same road that I've gone down. Which is really interesting. So if you want to communicate via email, I'd be happy to discuss what I find and some of the pitfalls that I've stumbled into, and etc. If you want to do that offline, that'd be great. I'm open to that. A couple of comments right off, which I'll throw out here. When you talk about and this is not specifically to you necessarily, but in general, people talking about electrodynamics. When you talk about an object in motion or an object's speed or an object's velocity, always remember that an object is always in all speeds. It has all velocities, all at the same time, unless you specify with respect to a specific mathematical coordinate system. Or you say that there is a preferred reference frame, a vacuum ether frame, and all velocities are with respect to that frame. It's just something that I've been meditating on for quite a while now. When people say, oh, this particle has a velocity or speed of so many meters per second. And I'm thinking, yeah, but I can do either a Galilean transformation or, go into any other reference frame, and that object can then have any speed that you want. So I'm starting to think, okay, when you set things up, you got to think that, oh, it's not just this speed, but it's all speeds, and it's all speeds all at the same time. And whatever the mathematics is and stuff, it has to be consistent with that. It's just throwing out a couple of ideas for you to consider. The other was something that you mentioned. I had it written down, but then you and Ian started talking a little bit about this, is the notion of fields. And what I found, I started doing a lot of Weber electrodynamics, a lot of the math, and I was trying to compare it to the Maxwell electrodynamics. And I came to a point after a couple of years of this, it took me a long time to get there, but it came to a point where I realized that there is a difference between the Euler system or approach and the Lagrangian system or approach. And it seems that Weber is expressed in a Lagrangian system, and that means that you have particle trajectories. So a position R vector is a vector of time. So you could say R is equal to R parenthesis T for time. And the Euler system or approach, which seems to be the Maxwell or standard today modern Maxwell electrodynamics, that's the Euler approach. And R is not a position of time. So the comparison, hey, let's compare Weber electrodynamics to Maxwell electrodynamics. You already start with a problem. Is that one is talking about trajectories and the other is talking about a fixed location in space. And a fixed location, you are going to try to evaluate what the field value is at that particular fixed position in space. Now you can go to another position or another position, but these positions are not functions of time. And so when you start taking in the mathematics derivatives with respect to time, you're doing things completely different in the Weber electrodynamics versus the Maxwell electrodynamics. So then when you start talking about Ampere's force law or Weber's force law, well, let's compare it to, what's used in the Maxwell's approach, the Lorentz force law. You've already started mixing apples and oranges. So just, think on that problem for a little bit. So if you want to do such comparisons, be a little careful. I don't think you can do straight comparisons. The question I have for you, though, is why you seem to be focused around Ampere's force law and not Weber's force law. Weber force law includes Ampere's force law, but seems to be a little more general, and you don't need to. Weber's force law is for, let's say, individual particle and individual particle or object interactions, from which you can build up an Amperian current element and obtain the Ampere force law. So I was curious why you're focusing, it seems, more on Ampere force law and not a little more general Weber force law. Is David still with us?
Yeah, I'm just sending in. We've actually lost David, and I'm just about. I better send him an email because it could have been something that I did or Franklin, but he might have disappeared himself. So if you give us a moment, I'll send him an email. He seems to be online, and say, "Would you please log in again?" Because it'd be better than having any of us second guess his view on what Bob said. Okay. Okay, so yeah, so I know you might appear to be favoring the Weber system, and yet you correctly say that perhaps we're speaking a bit at cross purposes, because in one case we're using the sort of Euler system, another Lagrangian. Although, by the way, some of the classical texts say that actually both systems are ultimately due to Euler. But however,
I would just like to see, I throw this out there, even though David's not with us necessarily and can't hear, throw it out to everyone else. I'm really surprised that this difference between the Euler approach and the Lagrangian approach is not emphasized in any of the electrodynamics texts. I'm just so surprised at that. It's almost like they,
as is the whole question that I raised about the convective derivative.
Derivatives, exactly. Yeah. But I open up some electrodynamics text and they start talking about, well, you got R and you got and I got is R a function of time in this text, or is it not a function of time in this text? And to be very explicit with the, and then of course in the equations for the magnetic field and the Lorentz force, you get these V's for velocities or speeds. It's like, with respect to what? What are they talking about? And it's not explicitly stated what they mean and what they're talking about. So,
okay, well,
it's very annoying.
Yeah, I don't know. Maybe there's some obfuscation in dealing with electrodynamics, which doesn't exist in other branches of applied mathematics. I don't know. But what we might do, Bob, with your permission, is note what you've said and get some comments from other members of the green room. And then, if necessary, for example, Vladimir wants to come in. I'll bring him in now. And then we might get David to summarize. And if necessary, I can, insofar as I can remember what some of you were saying, I'll prompt David. So is that all right? And if you want to come back, Bob, we can do that. Thank you very much. Now, Vladimir, so what's your brief reaction or questions or any other points you'd like to raise with regard to what has been said?
I would like to raise the question about Lorentz force. First of all, force, it's a classical notion. Velocity is a classical notion, but there is some notion charge. And still, I don't understand in a classical physics, what does it mean charge? Let me remind you about the Maxwell equations. In Maxwell equations, we don't have charge. We have only charge density. We have only energy density. We have only energy flux, and that's it in Maxwell equations. And Lorentz force and all this, it's outside of Maxwell equations. And classical notion, what does it mean charge? I still don't know. And then the next question, I talked about the absolute frame of reference. It was an absolutely right questions about what kind of velocity we put inside of this Lorentz force. It might be only absolute frame of reference. And we know there is some microwave background radiation. You can go against this basic frame, and that's it. then we don't have any questions about what kind of velocity we have. It was an absolutely right questions. Why we are so confused? Because, as I told you, we have some relativity. We are moving from one reference frame to another one, and we are confused which one is correct. That's why, continuing our talking about the classical physics and quantum physics, because usually in this Lorentz equations we have E means like elementary charge, but elementary charge belongs to elementary particles, and this is a quantum physics. There is no correlation between quantum physics and classical physics, because classical physics, it's ensemble of quantum physics, the quantum particles of quantum physics. That's why even the notion of charge, classical notion, it's not elementary charge we introduce for electron and from other particles. You see, it's not so easy. This confusion always between classical physics and quantum physics. And people, they're doing, especially in this case, force is a classical, speed is a classical notion, and charge, I don't know, what does it mean, charge? What do you think about it, guys, all of you? Because, it's very important, because for quantum objects, we have only 4 momentum. That's it. Forget about all the other issues. There are no forces for them, nothing. There are only 4 momentums, and that's it. That's why I want to know, what does it mean, charge? I want to know about the validity of the Lorentz force. For what? For whom to apply it? For quantum objects, it's not fair. It's not even the true. It's wrong.
So perhaps the quantum analysis has introduced another complication, into the whole study, which is really leading us, further astray.
Yes, but quantum physics, they don't have the notion of force. There is no force. It's a classical notion. That's why, this mixture between classical and quantum physics, it's my main concern. And most of the people, they're doing this mixture in their minds, in their equations, and they're trying to solve the issues. There are some contradictions between some different approaches because they didn't use the right approach. If you are in classical physics, please follow classical physics. If you are in quantum physics, follow quantum physics. That's it.
Yeah, I think there is something in that. They're not
right now, the definition of what contemporary physics is, it's a mixture between classical physics and quantum physics. It's exactly what is our confusion right now. Guys, let's stop it. Let's talk in the right language with the right definitions, notions, then we will be on the same page.
Well, let's note that again for perhaps the summary, if we can get David back, Vladimir. Thank you very much for that comment. And I'll bring it down for the moment. Thank you, indeed. Now, just wondering, James, have you any comment you'd like to make or a question? I know we don't have David at the moment, but I'm just trying to get everybody in on the green room. And I know you may have a comment.
Well, one comment might be the so-called infinite force when R in the divided by R squared force law, Coulomb force law gets to 0. And the way to resolve that is that it can't get to 0. You quantize space, and the binary mechanics length constant is the valid value for R. Period. That's all. Thank you.
Okay. I'm just going to take some notes about the various things, because if we get David back, I'll have to remind him on what we're talking about.
Another thought that occurred to me is all of the mentions of so-called paradoxes and puzzles and so forth are again supporting the need to question the theory that space and time are continuous. Thank you.
Okay, this is something I know you've spoken about, and you do, and thank you very much for raising that again. So I've noted that. I just put a continuous. as well. Thank you very much, Jim, for that comment. Thank you. So Harry Ricker is there, and again, he's probably just in the background because yeah, you're there, Harry. Well, Harry, we'd like to hear if you have any particular response to what David has been saying, or anything you'd like to put to him in the event that he comes back. He's not here at the moment.
I was kind of confused on one point. There's one point, and that is, it's my understanding that the Lorentz force law violates Newton's law, third law. Is that not what? Did I misunderstand that?
No, I think that has been said by people like Wesley, and I think David was concurring with it. I'm not sure. I'm not sure.
Yeah, that was a point that I wasn't really clear on.
Yeah,
but I think that the point that was made earlier about mixing up classical physics with quantum physics, I think that you ought to also be careful about mixing up relativistic physics with classical physics and quantum physics, because I think they're three different realms. And so when you're talking about physics, you're really talking about different paradigms, I think would be the word. They like to use the word paradigm to describe science, but I think within physics, you have all these different paradigms. And the point I would make about this is that there is a controversy about this particular, these different laws, the Grassman law, the Ampere's law, the Lorentz law. Okay. And you have to be careful about the context in which you're talking about. And I think that's pretty clear. And that's a point well made by the gentleman that made that point. And I think Bob Gray also made the point about the different mathematical methods have implied different assumptions and different, and you have to be careful about the different mathematics in the different contexts you're using. And we're not always clear about that. We just use the shorthand. We just say, such and such, the speed of the particle, because basically it's kind of difficult to go in and say, for every statement that you make, you don't want to say for this frame of reference, blah, 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 and make it complicated. We use a shorthand when we talk. That's another problem. Anyway, my question was about the Newton's third law of force being violated or not.
And Denny has just made a comment that even the elites agree that classical EM theory fails to obey Newton's third law.
Yeah, here again, what do we mean by classical EM theory? That's an amalgamation of what happened in the 19th century with respect to Ampere and Grassman and Weber. Okay, that's a different tradition in electromagnetic theory from the Maxwell tradition, which is the Faraday-Maxwell tradition. So you have two different traditions that you're talking about there. I mean, and as I understand it, there's a difference of opinion between people who adhere to the different traditions. Does that make sense what I'm saying? By tradition,
it could even be dependent upon the area you're in. Like 19th century mathematics, the British system and the continental system were opposed to each other in many ways, and people just had almost nationalistic sort of allegiances. And
that's another example of, I think that comes into play here between the Weber versus the Maxwell, because they're. You're exactly correct. There's this nationalistic difference of opinion there. And then, of course, you bring in Ampere, then you're bringing in French as a different
That's true. Yeah.
nationalistic viewpoint.
Indeed. Okay. Well, I think we've captured that. Thank you very much.
So Dennis is saying the Maxwell tradition is now believed by the elites. Now, I think they would like to say that. I think they would like to say that and believe that's true, but it's kind of hard to accept that when you have Coulomb's law, which is French, and then you have Ampere's law, and when you read the textbooks, they don't present it historically. And this is one of the things that confused me when I first started studying electricity and magnetism. They just tell you all these different laws as if they all make one consistent whole, but they're really basically different people working in different countries with different philosophies of doing things. And then the textbooks have amalgamated all this together, and they try to convince you that, yes, it makes a consistent whole. But then dissident critics come along, and they start finding holes in this amalgamate of attempt to make it all seem like it's a logical, consistent whole. And that's where a lot of the controversies come in, because it's pretty easy to find logical inconsistencies in mashing all this stuff together.
Right. It's a bit of a kaleidoscope. Well, okay. Thank you very much for that, Harry. And I'm going to, thank you indeed. I'm going to be in a difficult position, because I don't think David has come back, and I hope we haven't thrown him off, because by pressing the wrong button we can get rid of somebody, but I don't think we did. And I have sent him 2 emails just to come back, and he hasn't done that. So just before I try to summarize in my poor way, does anybody want to make any other comment in the green room? No. Okay, because we are sort of running out of time, and I think there just a few later comments. I'll just see anything there. I think Cornelis was in the green room, but he's left, I think, now, so you have to leave that. Okay, well, I think we're going to have to. You're going to have to put me in the hot seat, which I have been in, but it's been, quite a pleasant experience actually to listen to all these. There was a lot of material in the slides, and maybe a lot of the material was quite prolix and small, very hard to read. So as I say, we can supply more information later. It was a good overall introduction to the whole concept of marrying electrodynamics to Newtonian dynamics, in my opinion, and maybe making people aware of the work of the Graneaus, the father, Dr. Peter, I think it was Graneau. I think he was Polish originally, and he came to the United States. He might have been in the German area of Poland or something. He came to the United States and did work there. You can read his biography on the Science Database. And then his son Neal. I'm not sure. He may have been born in Britain, actually, because I think he was in. The father was in Britain for some time, but he's ended up in the University of Oxford. I was looking him up last night, actually. I couldn't find him in the list of the current lecturers there or academic staff, but he seems to be in the University of Oxford, and it's worth keeping an eye. And maybe if you can, getting the book of the Graneaus. It's only one of the books, actually, and it's nice to have a father and son collaborating in that way. So Neal was actually invited to today's talk, but as an observer or a contributor if he wished. But he's possibly away. He got no answer. But I was delighted to see that Andre Assis did come. He's in Brazil, actually, and he's a distinguished academic in this area. He's written a lot on it, and I would advocate anybody to check out his works. Some of them rather mathematical, but they're well worth studying. And I was delighted to hear that he was here, and he wasn't impressing his views upon us. He's done that enough in his papers. But so thank you all very, very much for your comments. Basically, Bob raised this whole question about the different concepts of, the Eulerian versus the Lagrangian way. Again, more nationality, Swiss, and I was going to say French, but I think Lagrange was an Italian originally, and I think he adopted French nationality under the Napoleonic empire. So I think maybe both countries claim him, and whether the radius vector r is dependent upon t time or not. And this is an interesting question of looking at things in different ways. And I think I'll have to look into this a bit more, because I was saying, well, this is merely just two different ways of looking at the same thing. But if they're giving sort of different answers, and if as Bob suggests, this hasn't been clarified sufficiently in electrodynamics, that is a major flaw. And it's something that'll have to be addressed in time. And then Vladimir raised this, and Harry also agreed that we've sort of like had a split personality, instead of dealing with things classically or in terms of quantum theory, say, we've sort of moving one or the other. We have a mishmash, a kaleidoscope of the two. And Harry said, we're doing this maybe with special relativity and pre-relativistic dynamics as well. So that can obfuscate the whole question, that we're not clearly sticking to one sort of set of postulates and seeing what flows from the postulates. We're moving around. And then Jim just reminded us of this business of the force maybe tending towards infinity in these sort of classical inverse square laws for gravitation or electrostatics or what have you, when r approaches zero. And this is something that maybe we've had to come into things like atomic theory and electrons and repelling each other and so on. So that is something perhaps for consistent theory that needs to be looked at. And of course, Jim also reminded us of his work in regard to looking at space as inherently not continuous, but discrete. And then the final chestnut, which I'd raised as well, but was raised by Harry as well, in more detail, about this whole business of Lorentz versus the Newton's third law. And they're saying, well, goodness me, maybe the Lorentzian system, or maybe the Biot-Savart sort of system, which is taught in academics, neither complies with energy conservation nor Newton's third law, which maybe amounts to the same thing, because if you contravene one, you're going to contravene the other. And then the whole question is it only kinetic energy, or is it total energy? If it's kinetic energy, well, in dynamics you have that's dependent upon v squared, whereas momentum is dependent upon v. And in electrostatics, you have, say, charge is dependent upon v, say, which is the voltage, whereas the energy is dependent upon v squared, which is the voltage. So you're simultaneously trying to conserve two, and maybe that's not possible, but that will have to be looked at. So there's a lot of material which has to be looked at, and I, for one, actually am going to spend some time trying to blow up some of the latter slides that David presented, and I'm going to have a look at some of those references. It's going to be quite a challenge, but I think that'll be interesting. Maybe I'll just put up one more. Okay, there's Cornell just says force tending to infinity assumes the force carrier has a linear respond to the level of force it carries. I didn't know if it was my fellow countryman or not, but this gentleman in the southwest of Ireland, Kev Con, he's been asking about the rugby or something between New Zealand and Ireland. He says I'm actually in New Zealand. He's obviously a Kiwi, but he's been in Ireland for 25 years, so it's a win-win for me tonight. So it's just a joke about that. Okay, well, so I'm sorry that David didn't have an opportunity of coming back and summarizing, but on behalf of the CNPS, I'd like to offer our very great thanks to him for taking the trouble to go through so much material. I know he's been supplying or he's been working on the slides for some time, and he's been sending notes about what do you think is better? Do you think I should have these colors, or do you think I should do this and the other? So he's been consulting with us a lot, and I think it worked out a lot. Actually, all I can say is you could easily have had a series of lectures on what he's said tonight. Today. It's coming in the evening shortly, but here. So we might think about this, and dependent upon the feedback I get, we may very well ask David to come back and maybe concentrate on one of the aspects that he has dealt with at a later stage. So I'll close the meeting now, and I'll just thank you all. We're getting very nice comments. You know, people normally are quite happy. Thank you to all. I'd like to thank you all for participating and giving David the backing that he needs, the interest he needs to pursue his studies. He's a working man. He's unlike many of us here who are retired, like myself. Maybe have a little more leisure. Although I don't know how I had enough time when I worked to pursue these things at all. You do know that I'm in the position of giving these talks every 2 weeks, or moderating the talks every week. So I'm working on a program for the rest of the year, and every other week we have Roger Anderson coming back. So I think he might be missing one of them. It could be next week, or there could be something next week, and maybe he's missing the next one. But you will be informed about that. I think he may be looking at part 2 to his talk last week about relativity again, and the lack of clarity thereof. I'll wish you all, wherever you are in the world. Most of you we're in the same time zone, I think, as David today, the Eastern Standard Time of the United States. I think he might be based in Florida at the moment. I wasn't clear about that. But thank you all very, very much. In absentia, thank you, David, again. Thank you all in the green room. Thank you all for your contributions. Thank you, Professor Assis, for attending. And goodbye. I'll wish you all a very good day. And I'll stop the broadcast now.